Okay, so we'll be going over section 4.8, Rolle's theorem and the mean value theorem. So, Rolle's theorem. Let f be continuous on the closed interval ab and differentiable on the open interval ab. If f of a equals 0 and f of b equals 0, then there is at least one point c in the interval ab such that f prime of c is equal to 0. Okay, so the conditions for which Rolle's theorem apply are important. Um, so for example, if this is A and this is B, then a function that did this would not satisfy the conditions. It says let f be continuous. This function that I've just drawn is continuous on the closed interval AB and differentiable on the open interval AB. This is not differentiable because of this sharp turn right here. We do have the f of A being 0 and f of B being 0, but it's not differentiable. So then Rolle's theorem does not apply, and although f of A is 0 and f of B is 0, there is no point in the middle where the derivative is 0. Right? We're losing the differentiable part. Now again, when I go over the proofs are to get you ready for when you're moving forward um, in your studies. And so we'll look at this in three cases, just a quick proof without too much detail. Just there's three cases, right? So if you have your AB is right here, and if you're going straight across, then that function is continuous, indifferentiable. It's a constant function. It's the function f of x equals 0. And then every point satisfies the conclusion uh, of um, Rolle's theorem. For every point in that interval, f prime of x is 0 because f of x is a constant function. Okay, so then suppose you didn't go straight across. If you didn't go straight across, then you must have gone up or gone down. Let's go over the gone up. If you went up, right, then you're looking at a continuous function on a closed interval that is differentiable on the open interval. And so then you're guaranteed by the extreme value theorem an absolute max and an absolute min. And not only that, you know that your absolute max and absolute min has to happen at the endpoints or the critical points, right? And since at the endpoints they're both 0, then it couldn't happen at the endpoints. So then it must have happened at the critical points. And since it's differentiable, there's no place where the derivative is undefined, and so it must have happened at a stationary point where your derivative was 0, like you have here in your graph, at a flat spot, right? Now, same thing is going to happen if instead of going up, you went down. If you went down, right, then you have a continuous function on a closed interval, and so and differentiable on the open interval. So by the extreme value theorem, you're guaranteed an absolute max and an absolute min. Since at the endpoints, and it's going to either happen at the endpoints or at the critical points. At the endpoints it's 0, so the absolute min could not happen at the endpoints, and so it would have to happen somewhere in the middle. You would have a critical point, but because it's differentiable, your critical point would have to be a stationary point. So your derivative would have to be 0. And so there you go. That's the proof of that. Now, these existence theorems seem kind of pointless because they don't tell you how to find the point, um, but they just tell you that the point exists. That's why it's called an existence theorem. At the end of the section, we'll see why they're important, right? So verify that the hypotheses of Rolle's theorem are satisfied on the given interval and find the values of C in that interval that satisfy the conclusion of the theorem, right? So I don't expect you to say too much. I mean, it should be obvious just by looking at this that f is continuous and differentiable. Right? You have the sum of two power functions. So they're continuous on their domain, and 0, 4 is in the domain of this function. So I don't expect you to say anything other than f is continuous and differentiable, right? So now the second part that it needs to meet is that it's 0 at the endpoints, right? And so then we just, f of 0 is 0. You can see that just by looking at it. You're going to plug in a 0 everywhere you see an x. So no need to show a ton of work there. And now f of 4, that one, put in 4 everywhere you see an x, and you get 2 minus 2, which is 0. So you get 0 on the endpoints. So then Rolle's theorem guarantees that there is a number somewhere in between 0 and 4. So somewhere in between 0 is less than c, which is less than 4, f prime of c will equal 0. So verify that therefore um, somewhere between 0 and 4, f prime of c equals 0. And then it says, and find all values of c in that interval that satisfy the conclusion of the theorem. So the conclusion of the theorem is that somewhere in between 0 and 4, the derivative is 0. So let's find the derivative and see where it's 0. So f prime of x is equal to the derivative of the first term is just 1/2. The derivative of the square root function is 1 over 2 square roots of 2. I'm sorry, square roots of x. And then we just figure out what makes it 0. We find the 0 is equal to 1/2 minus 1 over 2 square root of x. Right? We can add the 1/2 square root of x to both sides and get 1 over 2 square root of x is equal to 1/2. We can cross multiply. So 2 is equal to 2 square roots of x. We can divide both sides by 2, so 1 is equal to the square root of x. And then square both sides, x is equal to 1. Only thing is, when you square both sides of an equation, you have to check to make sure that it really works. And you can see that f prime of 1 is equal to 1/2 minus 1 over 2 times the square root of 1, which is 0. Right? And so there we go. You should pause the video and try the next one so that you're not just sitting there. Right? So verify that the hypotheses of Rolle's theorem are satisfied on the given interval and find all the values of c in that interval that satisfy the conclusion of the theorem. Right? So f prime of x. Oh, I'm sorry, we got to satisfy, show that it satisfies the conditions. Right? And so this is a little bit trickier because the natural log is only defined for positive values, right? And so then we have to show that this expression on the inside is positive on this interval, right? And so then again, what we can do is we can factor that expression. can begin by factoring out the minus. Then we can factor the trinomial. But when we do that, then we know that it has to be a plus and a minus. And then the only factors of 4 are 1 times 4 and 2 times 2. And those two will subtract to make 3, and those two will subtract to make 0. So then that means that this thing does not factor. Okay, so we tried factoring didn't work, right? And so then what we can do is find the zeros of the expression. So let me give myself some room. This didn't work. So let me go ahead and erase it. And so let's start here then. We have negative x squared plus 2x plus 4 equals 0. And so then we get rid of the negative, multiplying both sides by negative x squared. So negative x squared minus 2x minus 4 equals 0. Now you could use the quadratic formula since it's not going to factor, or because the first term is x squared and the middle term is even, you can complete the square. So we'll add 4 to both sides. And now we need to complete the square, right? So right now, it's not a perfect square trinomial, so we complete the square by taking this number, dividing it by 2, which gives us 1, squaring it gives us 1, and then we add 1 over here. And so we get x minus 1 squared is equal to 5. And so then x minus 1 is equal to plus or minus the square root of 5. And so then x is equal to 1 plus or minus the square root of 5. Okay, so then on the number line, and this is a sign chart not for f prime, but just for regular f. Actually, no, this is a sign chart for negative x squared plus 2x plus 4, right? And so then we have 1 plus the square root of 5 and 1 minus the square root of 5. And because this is a parabola that opens down, you should know that over here it is negative. In the middle it is positive. And then over here it is negative. Right? You should know that. Or you could test points if you like, but you should know what that graph looks like. 1 minus the square root of 5 is negative 1.23. Negative 1.24. Doesn't matter. And then 1 plus the square root of 5 is 3.24. And so then everywhere in this interval here, because we're only going from -1 to 3, it's positive. So somewhere in here is -1, and then somewhere over here is 3. And during that whole time interval, or during that whole interval, it's positive. So the argument of the natural log is positive in that interval, and so since you have the composition of two continuous functions, the function is continuous. So, and also since you have the composition of two differentiable functions, the function is differentiable. So f is continuous and differentiable, right? So verify that the hypotheses of Rolle's theorem are satisfied. So you have to show this work that I just showed to show that it verifies that because it's not obvious, right? You could have this expression here in the inside could have been negative, and then you're doing nonsense because you can't natural log negative numbers. So you need to be careful with that. But we showed it's continuous and differentiable. Now we need to show that f of -1 and f of 3 is 0. So f of -1 is the natural log of 4 minus 2 minus 1, which is the natural log of 1, which is 0. F of 3 is the natural log of 4 plus 6 minus 9. 4 plus 6 is 10, minus 9 is 1. The natural log of 1 is 0. And so then somewhere in the middle, the derivative has to be 0, right? Therefore, there's a c in the interval from -1 to 3 such that f prime of c is equal to 0. So now we have to find it. First we have to find the derivative. F prime of x is a composition. So we get 1 over the inside, 4 plus 2x minus x squared, and then times the derivative of the inside. So in the numerator we'll have the derivative of the inside, 2 minus 2x. What we've already seen is that in the denominator you have the argument, and we already seen that this expression is 0 at 1 minus the square root of 5 and 1 plus the square root of 5, right? So the derivative is undefined there, but we're not looking at those numbers. We're looking at what makes the derivative 0. And so the only thing that makes the derivative 0 is what makes the numerator 0. 2 minus 2x has to equal 0. So then 2 has to equal 2x. So then x has to equal 2. Well, this is what makes your derivative 0, and that falls in the interval from -1 to 3. And so we're good there. Moving on to our next theorem. And so then again, this gives you a little flavor of the discipline. The mean value, and Rolle's theorem was pretty simple to prove, and so the whole point of Rolle's theorem is to then allow you to prove this next theorem. This is just a generalization of the mean value theorem. I'm sorry, of Rolle's theorem. This is called the mean value theorem, and its main purpose is to help us prove some very powerful, useful theorems that we've already come across and that we're going to come across. Okay, so the mean value theorem says let f be continuous on the closed interval AB and differentiable on the open interval AB, and then there is at least one point C in AB such that f prime of C is equal to f of B minus f of A, all divided by B minus A. Right? So then it has a very, very nice geometric interpretation. In chapter 1 we talked about this a lot. F of B minus f of A all over B minus A, and that is just the slope of the secant line. And what f prime of C gives you, we've been using over and over in this class, is the slope of the tangent line. And so then all this tells you then is if you have a continuous differentiable function on the closed interval, then somewhere in the middle, the slope of the secant line is equal to the slope of the tangent line. And there's a very nice illustration here that they're drawing here for you right here. They draw the secant line and the tangent line, right? And if you draw this picture, it seems fairly intuitive that you can do that you can take this and slide it up, that you can take this line right here and slide it until you get a point of tangency. Now, why is this a generalization of Rolle's theorem? Well, in Rolle's theorem, since the endpoints were the same and since they were both 0, then f of b minus f of a would be 0, divided by b minus a would still be 0. And so the slope of the secant line would be 0, and the slope of the tangent line would also be 0, right? Okay, so I won't go through the entire proof, but it is kind of nice to see how these work, right? So the whole point of Rolle's theorem was to allow us to prove this theorem. So how can we use Rolle's theorem to prove this theorem? Well, what we do is we build a function that satisfies Rolle's theorem. Now, this isn't at all obvious, but here's what we can do. This is a tangent line, right? The equation of a line is given to you by y minus y1, and I'll use the f of b as my y1, is equal to my slope, which is f of b minus f of a, all divided by b minus a, times x minus x1. Right, so the x value that correspond to this one. And so then this becomes y is equal to f of b minus f of a, all divided by b minus a, times x minus b, plus f of b. And we're going to go ahead and just call this y secant. So this is just the secant line, right? And so then the clever thing that somebody came up with is that they could then look at this function, h of x, which is going to be f of x minus y secant, all of this so I don't have to keep writing it. Now, f is continuous and differentiable, so y secant is continuous and differentiable, so h of x is continuous and differentiable, right? Now, when I put in b into this formula, then h of b will be f of b minus, and then when I put b into the secant function, I get, when I put b into the secant function over here, I get f of b. And so I get 0. H of a, when it will be f of a minus, and when I put a into the into this formula right here, because that's my secant function, then I get f of b minus f of a all over b minus a, but over here I will get a minus b. So I will get a minus 1 out of this. Out of these two right here, I will get a minus 1. That will give me minus f of b. Plus f of a. And then I still have the plus f of b. You can see then that the f of b's will cancel out, and you'll have f of a minus f of a, and you get 0. And so then this new function that we just made, h, satisfies the conclusion of the mean value theorem. And so then, I'm sorry, not the mean value theorem, Rolle's theorem. So then Rolle's theorem applies. And so since Rolle's theorem applies somewhere in the middle, h prime of c has to equal, well, the derivative of the first term is f prime of x. Sorry, let's just go ahead and call this h prime of x is equal to f prime of x. And then the derivative of the secant is just the slope of the secant line. And so then we get f of b minus f of a, all divided by b minus a. Okay, but then somewhere in the middle, by Rolle's theorem, there has to be a c where your derivative is 0. And so then we can put that c in. So then h prime of c, which is just f prime of c minus f of b minus f of a, all divided by b minus a. And that has to equal 0. And so then there you have it. Once you move this term over, you get that f prime of c is equal to f of b minus f of a, all divided by b minus a. So that's how that goes. Again, that's just introducing you to the to the discipline. In case you're wanting to go on to math, this is the kind of things that you will be doing. It will stop being computational and start being more about proving things, and how you get better at it is by looking at other people prove things, and then you practice proving things. Not the most important part of this class, but it does develop your mathematical maturity. So you should try to follow along, but if it's over your head a little bit, then do the best you can. So verify that the hypotheses of the mean value theorem are satisfied on the given interval, and find all the values of c in that interval that satisfy the conclusion of the theorem. So this function is continuous and differentiable, and that's all we need. So just make a quick statement. F is continuous and differentiable. So then we're ready, we're good to go. And find all the values of c in that interval that satisfy the conclusion of the theorem. Okay, so how you're going to remember this is just to remember that all the mean value theorem says is that somewhere in between -1 and 2, the slope of the secant line is equal to the slope of the tangent line. So let's look at the slope of the secant line first, right? It's just the regular slope that you're used to, It's the change in y, f of 2 minus f of 1, all divided by the change in x. Sorry, f of 2 minus f of negative 1. 2 minus negative 1, right? When you put in 2, you get 8 plus 2 is 10, minus 4 is 6. When you put in negative 1, you get negative 1 minus 1. Negative 1 minus 1, that's negative 2 minus 4 is negative 6. And then 2 minus negative 1 is 3. 6 minus negative 6 is 12 divided by 3. And so 12 divided by 3 is 4. So somewhere in between negative 1 and 2, we're guaranteed at least 1 point, maybe more, where your derivative is exactly 4, where the slope of the secant line is equal to, and you might want to label that slope of the secant line. Where somewhere where the slope of the secant line is equal to the slope of the tangent line. So for the slope of the tangent line, that is given to you by the first derivative, which is 3x squared plus 1. Okay, and so this gives you the slope of the tangent line. And somewhere in between negative 1 and 2, the two have to be the same by the mean value theorem. So to find out where they are the same, so you just set them equal to each other. 3x squared plus 1 needs to equal 4. So then 3x squared needs to equal 3. So then x squared needs to equal 1. And so then if we square root both sides, remember that we always get a plus or minus 1. So that's all we were being asked to do. And we move on. Again, you should try this problem on your own. Pause the video. Make sure that you can do it. Look at the video. See how I did the problem. See how you did the problem. Make sure that they match. Verify the hypotheses of the mean value theorem are satisfied on the given interval and find all values of C in that interval that satisfy the conclusion of the theorem. Okay, so verify it. Well, you're definitely looking at a continuous function on its domain. The problem is that with this 1 over x, 0 is not in the domain. But if you look at your interval, we're not looking at 0 anyway. So we're good, right? And so no work to really show there. That's pretty obvious by inspection. F is continuous and differentiable. And that was it. And so now we're ready to go. So again, slope of the secant line is f of 4 minus f of 3, all divided by 4 minus 3. When you put in 4, you get 4 minus 1/4, minus, when you put in 3, you get 3 minus 1/3, and 4 minus 3 is 1, and we don't have to write that. So 4 times 4 is 16, minus 1 is 15, so the first one is 15/4. 3 times 3 is 9, minus 1 is 8, minus 8/3. The common denominator is going to be 12. So 15 times 3 is 45 over 12. 32 times 8 times 4 is 32 over 12, which gives me 13 over 12. Okay, so the slope of the tangent line, just take the derivative, is f prime of x. Two terms. The first term, derivative is 1. Second term, it's better to write it as x to the negative 1, 1 plus x to the negative 2. So when you bring down the exponent, that makes this minus a plus. Take 1 away from the exponent, you get an x to the negative 2. And so then somewhere in the middle, 1 plus x to the negative 2 has to equal 13 over 12. Get rid of the 1. 13 twelfths minus 12 twelfths is 1 12th. And then get rid of the negative 2. And we can get rid of that by raising to the negative 1/2. Because then when we multiply the exponents, we will get just an x. But when we raise the 1/12 to the negative 1/2, the negative flips it and gives us the square. Gives us the 12. The 1/2 square roots it. But when we're using this 1/2, there's always a plus or minus because that means we're square rooting. Okay, and plus or minus, but we're only looking in the interval from 3 to 4, so we're not using the negative. And the square root of 12 is in between 3 and 4 because 3 squared is 9 and 4 squared is 16. Okay. So you are traveling westbound on Avenue 12, where the speed limit is 55 miles per hour, although I think lots of people have forgot that. An officer clocks you traveling 55 miles per hour. 10 miles down the road, and 10 minutes later, you are clocked by a second officer at 55 miles per hour. The second officer pulls you over for speeding. Why? Okay, so pause the video. We've just gone over the mean value theorem. And so then you should try and see how the mean value theorem applies and if you can apply it on your own. And then come back, right? So again, all the mean value theorem says is that the slope of the secant line is equal to the slope of the tangent line. Somewhere in your interval, right? So the slope of the secant line is your average rate of change. You traveled 10 miles in 10 minutes. You traveled 10 miles in 10 minutes. So your slope of your secant line, how fast you went over that interval, is 10 miles in 10 minutes, which means you were going 1 mile per minute. And if you multiply that by the fact that there are 60 minutes in 1 hour, then you were going 60 miles per hour at least at one point in your interval. Maybe faster, maybe slower, but at least at one point you were traveling at 60 miles per hour, right? So, which has to equal your instantaneous rate of change, right? So for at least one point in your time interval, you were going at least 60 miles an hour by the mean value theorem. Maybe faster, but at least going 60 miles an hour. So let's move on. Okay, so The mean value theorem is an existence theorem. It tells you that something exists. It doesn't tell you how to find it, doesn't tell you anything really about it other than it exists, right? And so then that may seem kind of pointless and useless, but really in mathematics, the point of it is to help you uh, uh, prove other things, right? Other thing is there's no point in looking for something if it doesn't exist, right? So if you can show that something does not exist, then why go looking for it? It doesn't exist. But um, here's how we're going to use it. We're going to use it in chapter 5 for a very important um, result, but we've already gone over this result, theorem 4.1.2. This was a very intuitive result, but we did not prove it because we didn't have what we needed to prove it. But now that with the mean value theorem, we can prove it. So this says, let f be a function that is continuous on a closed interval, ab, and differentiable on the open interval, ab. If f prime of x is greater than 0 for every value of x in ab, then f is increasing on b. Okay, and so if f prime of x is less than 0 for every value of x in ab, then f is decreasing on ab. And if f prime of x is equal to 0 for every value of x in ab, then f is a constant on ab. I think all these things are intuitive if you recognize that the derivative represents the slope of the tangent line. And so I think that they're intuitive, but we didn't prove it. We just used our intuition and our pictures and said, yeah, that this should work. But now we can rigorously prove it using the mean value theorem. So let's prove B. A is proved in your book, and it's very similar. Okay, so then let A be less than x1, which is less than x2, which is less than B, right? We're assuming that f prime of x is less than 0 for every value of x in AB. So x1 and x2 are in AB because I'm telling you that A is less than x1, and then x1 is less than x2, and that x2 is less than B. So both x1 and x2 are in AB, right? And so then by the mean value theorem, there exists a C such that f prime of C is equal to f of x2 minus f of x1, all divided by x2 minus x1. And f prime of C is less than 0. Okay, so then that means then that f of x2 minus f of x1 all divided by x2 minus x1 is less than 0. And then if we multiply both sides by x2 minus x1, which is positive, because x2 is bigger than x1, this preserves the inequality, so that f of x2 minus f of x1 is less than 0. And then if we add the f of x1, then we get that f of x2 is less than f of x1. So what we have just shown is that if you take any two numbers in between a and b where x1 is less than x2, then f of x2 is less than f of x1, therefore decreasing. That's what it means to be decreasing. That the a bigger input has a smaller output, right? Um, the same thing is going to happen for C. So for C, you're going to choose an x1 and x2 between A and B, and so then the slope of the secant line, f of x2 minus f of x1, all divided by x2 minus x1, will have to equal f prime of c for some c in between them, but f prime of c is 0 for everything in that interval. And so then you can go through the algebra, multiply both sides by x2 minus x1, and then add the x2 minus x1 and show that f of x2 will be the same as f of x1. And then what that shows is that it is always the same thing, and so that means it's constant. Okay, this is going to be this third part C is going to be useful in the next chapter, where we start talking about antiderivatives, and antiderivatives are going to be functions whose derivative is the function I gave you. We'll get there, but this theorem here is going to help you with that. If f and g are differentiable on an open interval, and if f prime of x is equal to g prime of x in that interval, then f minus g is constant on that interval, right? That is, there is a constant k such that f of x minus g of x equals k, or equivalently f of x is just g of x plus k for all x in that interval. Okay, so again, so if f and g are differentiable on an interval, and if f prime of x is equal to g prime of x for all x in the interval, then f minus g is constant on the interval. So what we've already shown is that if the derivative of a function is always 0, then that function is constant. So what we can do is we could let h of x equal f of x minus g of x. Then h prime of x will equal f prime of x minus g prime of x using our derivative rules, right? But then when I take this derivative, but I was told that f prime of x is the same thing as g prime of x, so then f prime of x minus g prime of x has to be 0. And so then that tells me then that h of x has to be a constant from our third theorem, from our third part of the last theorem. Therefore, h of x has to equal some constant. And so then f of x minus g of x, because that's what h of x was, has to equal a constant. And so then f of x has to equal g of x plus some constant. And there's the proof. Use the constant difference theorem to show that if f prime of x equals g prime of x for all x in the interval from negative infinity to infinity, and if f of x naught minus g of x naught equals c at some point x naught, then f of x minus g of x equals c for all x in that interval. Well, I think this directly follows from the theorem, right? The theorem tells us that if f prime of x equals g prime of x for all x in the interval, then f of x minus g of x is a constant. And so then that means it never changes. So then if its value at x naught is c, then its value has to always be c. To me, that's obvious from the theorem. So I'm not exactly sure why they put that there, but I mainly chose this problem to go over part B. Use the result in part A to show that the function h of x equals x minus 1 cubed minus um, x squared plus 3 times x minus 3 is a constant for all x in the interval from negative infinity to infinity, and find that constant. So here we can let f of x equal x minus 1 cubed, and g of x equal x squared plus 3 times x minus 3. We can find f prime of x, bring down the exponent, take 1 away from the exponent, times the derivative of the inside, but the derivative of the inside is 1, right? And so then this is 3 times, well, that's fine. We'll leave that there. Over here, g prime of x, product, so we need the product rule. The derivative of the first factor is 2x. Second factor left alone, x minus 3. Then the derivative of the second factor is 1 times the x squared plus 3. Okay, and so then if we distribute, we will get 2x squared minus 6x plus x squared plus 3. So then we will get 3x squared minus 6x plus 3. So then we will get 3 times x squared minus 2x plus 1, which is 3 times x minus 1 squared. So it says use the result in part A to show that the function is constant for all x, and find the constant, right? And so what I've just done is shown that they have the same derivative. This was my f, this was my g, and I found that they have the same derivative. Okay. Therefore, x minus 1 cubed minus x squared plus 3 times x minus 3 is equal to a constant. Now, how do we find the constant? And if f of x naught equals g of x naught, I'm sorry, and if f of x naught minus g of x naught equals c at some point x naught, well, since it's a constant, we get the same output from any input. So the easiest input that we could pick, I'm thinking of a couple. 3 would make all of this 0, and 3 would be easy to evaluate here. So h of 3 would be 3 minus 1 is 2, 2 cubed is 8. And then over here we would get 0. So therefore, this equals 8. Therefore, h of x is always 8. And there you go. So your homework for section 4.8 is 1 through 25 odd. I will be uploading uh, more more videos on Tuesday, and then we will review next Thursday. I will go through some sample problems and review for you, and then um, we will have spring break after next week, and we will have an exam when we come back from spring break. Stay safe. Please keep up, and we'll see you when we see you.